Let's get started. Thank you for showing up tonight. Really appreciate it. I think we have a nice program for you tonight. We have, we will start first with Hendrik from Netapp, who will tell you a story about cloud native projects, followed by Xavier, Professor X. I forgot to ask the right pronunciation, but really smart guy from Lunatech, who will tell you about Tensorflow and Scala. And then we started the workshops. So we have 2 locations. So just a question, who is here for the Angular workshop? Yeah, right. And who's here for the Scala workshop? Yeah. So what we will do is the Scala workshop will be here. For the Angular people, you can go there to the left, past the toilets. So if you want to know where the toilets are, they're on the left. And yeah, let's have go to nice workshops. So let's start first with Hendrik. Please give applause for Hendrik from Netapp.
So before I get started, who's developing software that in the end runs in containers? Or running containers otherwise? Because that's what I'm basically talking about. Not a particular new approach, but an approach that's getting more popular on how to turn your code into a container and bypass some of the issues you might otherwise run into. I keep this short. My name is Hendrik. I'm what we call a solution architect for DevOps, which essentially means I'm paid to spend time on containers with Kubernetes and OpenStack and Ansible and Terraform and a number of other topics, which is quite nice because I like doing that and I get paid for it. We're here at Netapp. What we do is focused around data management in hybrid cloud environments. So we try to bring data to wherever it's needed, which is one of the pieces that is often missed, because at least in a container you can easily move the application to some other place, right? And it's guaranteed to run the same way. That's the nice thing about a container, but you need to bring the data as well, and that's kind of the problem we try to address. So from source code to container, this is kind of what I'm going to talk about. And in order to start that, well, we probably want to talk about running that container in the end, right? Because we want to do some testing and all that. But for the moment, let's focus on going from source code to the container image. And for that, just a quick overview on what is a container image anyway. And essentially, this is standardized for quite some time now, based on the work that Docker has originally done. But it's OCI images now. So the Open Container Initiative has an open standard on what a container image looks like. And essentially, it's a metadata file, and then a number of layers in that container. And each layer is essentially just a tar file. So it's just a file system packed together, right? And then if it is a nicely designed container, you have kind of your base layer, which is what we would call the operating system, Alpine or Debian or whatever it is. Your runtime, your Java environment or Python or whatever, dependencies, libraries, and then the application, right? And that would be a nicely designed container, ideally. The original way to create a container was through a Docker file. So just a text file that is the instruction on how to create that container. And then you would run docker build, and it would look at that Docker file, and each line in that file creates one of these layers in the image, and that's how you end up with your container. There's a couple of issues with that. The first one is security, because in order to do that, you need to run Docker directly, and Docker runs as root. So that's okay on your developer workstation. That's probably not okay in a shared environment, because every developer working on that same shared environment has to run something that runs as root. It's probably not what you want. Another issue is around scalability, because you can not really run that in parallel a lot. And you can also not really make good use of that layered approach of the container image. because Docker build is just recreating the whole container every time. Right? It's not really making use of the fact that some of these layers might not change at all. It's just recreating them from scratch every time. That's how it works. And then it can be quite complicated to create a good Docker file. And most of them are not good, that you will find. Right? Because it's really important what the order of instructions in that file is, because that impacts how these layers are built. And so you have to take care of that. And then people try to bypass that to some extent by just combining a bunch of commands into one, basically using an ampersand and running a ton of commands in just one sequence to make it one layer, and download stuff to build and then clean it up again so it doesn't end up in your final container image and all those kind of things. And it's really not nice, right? So for quite some time, people try to bypass that. And the first iteration of that is just alternatives, and I'm not going to cover any of this in detail, but alternatives instead of Docker build. They still use the Docker file, so we don't really get rid of that. But the nice thing is, if you have a Docker file already, you can just plug that in and use that. Right? You don't have to change anything to your environment. And they at least get rid of the requirement of running it as root and all those kind of things. Right? So if you still want to use a Docker file, these are some of the more popular projects in that space. Probably go for one of them. And then there's some solutions that don't use a Docker file, and some are language specific. Some of them require other specification files, so you have to learn something new, which is not too nice in the end, probably. And then there's things like build packs. And that is really trying to make it easy, so you don't have to care about that at all. You don't have to come up with how these layers are built. You have to stand up for that, and it's all happened automatically. Right? And that was originally developed by Heroku. Anyone familiar with Heroku? Some? So it's a platform as a service, and you just give them your code, and they turn it into a container and run it on the platform. So they really needed a way to do this. Right? That's why they come up with the idea for what we now call build packs. They have a couple of advantages. So first, it's reusable, right? You come up with a generic way of building Java or Python or whatever language you prefer, right? And you can reuse that for every application. Which is also good because not every single developer has to start again all over, right? You come up with a ton of different solutions because everyone has different preferences, right? So it's all common across the whole environment. That also gives you a lot of security because all these base layers, your base layer, your OS layer, your runtime layer, your dependency layer, they all look the same because they were all created from the same build pack. It is a very modular approach, so you don't really have a build pack for Java. You have a build pack for the Java runtime, a build pack for the JDK, a build pack for Maven or Gradle or whatever you use, right? So it's modular to that level, and you can easily change some of these pieces in between, depending on what you need. And it is really fast because it's making use of this modular approach. So build packs only recreate the layers that change. So if the JDK didn't change, there's no need to rebuild that layer. The only change was in your application layer, so it only rebuilds that part of it, and then assembles a new container out of it. Right? So it's a lot faster, especially if you need to make changes at one of the lower layers. So for example, you need to change something at the OS layer to fix a security issue, and you need to do that across 500 containers. It's really easy to do that with build packs and really fast. Whereas with a traditional Docker file, you would need to rebuild 500 containers from scratch. So as I said, Heroku was the first company that came up with that idea in 2011, so quite a while ago. It's not exactly new. They developed that and came up with what they call version 2A, and at the same time Cloud Foundry thought that is a nice idea, and they kind of copied it. It was similar but not the same, so it's version 2B. And then they decided that it might be good to join forces and come up with a common open standard for it. And that's what we call now build packs. So version 3 of it is build packs. It's a sandbox project from the Cloud Native Computing Foundation. So it is an open standard. it's still mostly driven by Heroku and Cloud Foundry, or Provision at this time, because it's based on their work. And what build packs actually provide is just the API in between. So the lifecycle, this is where the build process actually happens, and then we have the platform to the left, which is your tooling, your interface to it, to work with it. So there's Pack, which is the native CLI tool from build pack from the project that they provide. There's one for Kubernetes, Kpack. There's different platforms implementing it, so you can do that on Google Cloud if you want to. That's Google Cloud Run. You just push in your code and they turn it into a container. Well, that's build packs in the end. You don't get to see it, but it's based on build packs. Right? You can do that in the Tech10 pipeline, which is a CI/CD tool, Kubernetes native one. We at Netapp actually do that in our Kubernetes service. I'm going to show you how that looks like later on. But you have one of these platforms that make use of it, and they are kind of specific to that implementation, but they all work across the same API specification here. And then on the other side, you have the build packs, which is just containers in the end that handle the process of building the image layer that they're responsible for. And you could do that yourself and come up with your own build pack if you really want to. Probably don't want to do that. So you use one of the build packs available for the language that you develop in. Right? And those come from Heroku, Cloud Foundry, and a number of other people that contribute them. But it's not something that the build pack team or project is actively developing. They only come up with a specification, and then others are developing the actual build packs and the actual platform to run them. Right? And then what happens is you have different stages, and the first one is the detect. So build packs go in and figure out which language it is, and from that figure out which build packs you might need. So they look at the code, and if they find like a package JSON, this okay, this looks like Node.js with NPM. Okay, so we need Node.js, we need NPM. If they find a POM XML, it's okay, this looks like Java and Maven. Okay, so we need the build pack for Java and one for Maven, and so on. So they try to automatically identify what language this is and what you need in the container in the end. That, of course, not always works, so you can influence that if you want to. There's different ways to do that, but the way that Heroku came up with, which probably is going to be the standard way in the end, is through a special file called a proc file, just a text file where you specify, okay, it's this language, and this is the main executable that needs to be executed in the end. And it's not mandatory to do that, so in many cases it just automatically identifies it, and that's all fine. But if you need to influence or want to influence that, that's possible as well. Then it analyzes what has changed compared to the last build. And by that it figures out which layers need to be rebuilt and which not. And most of the time only a small change happens, so most of the layers can stay the same. And then it's pulling them from a cache instead of rebuilding all the extra layers in the container. It's going through the build, it's exporting them to the registry, and only the extra layers, not the full container image at that point. And then it updates the metadata for that container image. So it points to the new layers that you just created, right? Which is what they call a rebase instead of a rebuild for the old container. I'm going to show that in like the next slide or so. And then it puts all the layers that it recreated in a cache for the next build. So it's really efficient to go through, CI pipeline and constant rebuilding because it caches as much as possible. Right? So what happens in that rebase is, say you have your registry, and in that registry what you actually have is the manifests. This is what we would consider to be the container image, but it's just a small file, like 1 kilobyte or something, that has some metadata for that container image, and then that points to all the different layers that make up the container. And say you have 3 different applications in there, they all use the same base layer, so they all point to that, and then they point to their application-specific layers. And all of that combined makes up that one container. Now, say we have a security issue here at the OS layer, which is where it typically happens, right? And you need to fix that. So traditionally you would have to rebuild all of the containers. With build packs, what's going to happen is you rebuild the OS layer with the patch in it, and then you only update these manifest files. So the only thing you need to upload for the registry is this one layer that has changed, really small change. And then you update these manifest files, a couple of kilobytes, really easy, which shows up as a new, completely new container, but it's just repointing to that layer, and everything else stays the same. And then, depending on what container runtime you have in your environment, if it's container D, it's clever enough to only pull that change. So even in your runtime production environment, you only need to pull that one extra layer instead of pulling all the container layers again. So it's really easy and real fast to, update hundreds of containers at the same time in a big environment. That's one of the big benefits. Right? The reason why all of this works is that we have, at least in Linux, we have API compatibility. So that's the application binary interface, and Linux guarantees that you can update any of the OS part without impacting the application itself. So we can just swap that out, and the application will still work. So what I'm going to show you in the demo is the way we implemented that in our Kubernetes solution. And we do a little bit more than just build packs to just turn it into a complete solution. So what's going to happen is that I'm doing a git push, I'm updating code in the repository. That triggers a webhook to the Netapp Kubernetes service, so we get notified of the push event, which then triggers a Tecton pipeline. So just a CI/CD pipeline native in Kubernetes that gets the code from the GitHub, runs the build pack. So in this step, all the analysis and auto detection and build stuff happens, and then deploys that to the cluster. And in the end, we have a URL and we can access the application. So that's kind of a quick overview of what I want to show you. Now let's see if that works. Any questions on that before I switch over to the other laptop? Yeah, all good? Has anyone worked with build packs before? Or with Cloud Foundry or Heroku or? No? So, the screen resolution is not perfect, but I hope you can see it. So that's kind of the interface for the Kubernetes service we have. I already deployed one cluster, but just to show you what that looks like. So the idea for that is that we can provide Kubernetes clusters in any environment, so any of the clouds, or on-prem on either hardware from us, so server, storage, network, all in the box, kind of Kubernetes in a box solution, or just any VMware you provide. Right? So we don't want to make this dependent on our own products, on our own hardware. You can run that on any VMware or on the cloud. Say I want to pick AWS, select the number of master nodes I want to have, right? Number of worker nodes I want to have, and I can always add more nodes, remove nodes, all that. Right? I'm going to keep this small just to keep costs down for me. So that's why I deploy in US West, because that's the cheapest region in AWS as well. It proposes a name, a VTuber, that's nice. I go for that. It's great in cluster for me. So in case you ever deployed a Kubernetes cluster before, this probably was harder than this, right? it takes about 4 or 5 minutes now to build that cluster, so that's why I prepared one. We're going to use that one. What we can do in that cluster is that we set up projects with, essentially in the end, is a namespace in Kubernetes, and it gives us the ability to run this application lifecycle management that I just talked about, which is based on Lunatech in the end. So we add a project here. Let's call that demo. You can set some quotas for that. I'm just going to leave that at the default, but if you want to limit that in any way, that's of course possible. And then we add an application to that project. And now it wants to know how to connect to my code repository. So give it my GitHub repository that I want to work with, and I give it a private SSH key, because in the end it reaches out via SSH to connect to GitHub. And then I can define a little bit on how I want to update it and how many replicas I want to have and all these kind of things. Not really important for this demo, but I can control all of that and create that. So what I now get is everything I need to set up the webhook in GitHub. So I get the URL that GitHub should call, and I get the secret for that. So let's copy that. We move over. This is the little demo application. Really nothing fancy, but we go to the settings here. This is the SSH key. So this is the public key. The private one is what I just entered in the setup. Right? So that's something I had prepared in advance. And then we can add a webhook. Give it the URL that was just generated for us. We want to have that in JSON, and we need the secret. So let's copy that. We are really interested in push events, so that's what we want to react to. So we just add that hook. And what GitHub is doing, it just sends a test notification to us. And that has a green check mark, so that worked, everything's fine. Right? We can go ahead. So let's do a commit and push that. And this is the application in the end. Again, not fancy, so I'm not going to focus on any of the code. But we should see that, yes, there's another hook that was triggered. Right? That's just because we did the git push. That now triggers the build pack process in here. So you see a ton of logs if you want to go for that. Or if you want to go for CLI, we can actually take a look at what's going on. So we have a namespace demo that was created for us when we set up the project, because that's the name we have given it. And we see a pod running in there. That's actually the build pack running now. Setting everything up. Let's check, so that one is completed, which means the whole build process is done already. Right? It uploaded the container image to an internal registry that we provide. So that's all working, and it's creating the final container with our application. Check again, that's running, so our application is just deployed to the Kubernetes cluster. And want to access that application, we get the link to it directly here, assuming that it is a web-based application. And yes, we get our application, which really just retrieves weather information for any city I give it. So, I give it Amsterdam. It tells me the current temperature, which doesn't really look right. Unless something has changed in the last hour or so. So let's see why that happens. You might have to take a look at the code. Oh, it's using parallel metrics units. Who's doing that? Nobody in Europe, right? Well, the UK, we are metric. So let's change that, and it's really just reaching out to a website and fetching the weather information. Right? So I changed that API call to metric. So we change that, we push it. We can take another look at the GitHub site. Yes, it notified us of it. If we want to follow what's going on, we can also take a look at the Kubernetes side. And we see there's another pod running. That's again our build pack process running in here. Right? And when that is completed, it's going to replace this one, the master. That's the actual application running. It's going to replace that with the new container image. Let's wait for that to complete. Yeah. So the build pack is done. It's terminating the old container and creating the new one. That looks good. So let's refresh this. Oh, it doesn't look too good. Better. And that looks a little bit better as well, right? So that's really it. Just a quick overview on build packs and just a demo of how we implement it. If you have any questions, let me know. I will be around for a while. Otherwise, enjoy the evening.
I'll give it up for Hendrik. Interesting talk.
Okay, thank you. So we have 12 minutes now. So it's a 45-minute talk that I usually, no, it's a 1 hour and a half talk that I usually squeeze in 45 with less than that. So we'll try not to show code, just some principles, and if you want to show code, you go to the workshop, or you go to the Angular workshop, and you can do TensorFlow in JavaScript, so there is no issue going one or the other. So I'm Xavier from Lunatech. We're a service company in Amsterdam, Rotterdam, Paris, and Belgium, doing mostly Java, Scala development, but also big data, machine learning for enterprise. So if you want to talk to someone, you will go at that table. If you're more interested in tech stuff here, yeah, everyone has this job, and here today is to talk about machine learning. So usually when I give talk to IT audience, people are not so familiar with machine learning, right? Yes, everyone comfortable with machine learning here? Yes. So I usually introduce a few concepts for machine learning, then talk about what kind of environment you would work with to do this machine learning stuff in Scala, and then talk a bit about TensorFlow framework itself, which is basically a set of low-level libraries to do linear algebra. That means heavy floating point computations for machine learning, and then you have, a few libraries in different languages on top of that: JavaScript, Python, Golang, Java, and Scala, whatever. Because we're talking about Scala, and we want to maybe use the machine learning result for something. We want to set up a web service in Scala that will allow us to consume some machine learning models, and then blah blah blah. Okay, so who is familiar with machine learning really? Here. Okay, so wake up, people. Okay. So it may sound like magic, but it really is not. The idea is just that you have data sets, right? And because it's a lot, and you want to be able to summarize it in something much more compact that is able to tell you something about the data, you want to compute something that is actually a function. And this function is supposed to represent one facet of the data. In more detail, your data set, let's say, is price of properties with a few features for these properties, like habitable surface, the surface of the land, the number of bedrooms, number of sidings. That's a few things you may have about houses, right? It's a table. You have rows and columns, and all those things you want to transform one or another into numbers. Okay, so you could model this thing, because you're doing object-oriented stuff, you do structs, because you do engineering. When you do machine learning, you're just manipulating floating point numbers because it's mathematics. Okay. So between the two, those are the engineering side of modeling data, but in the end it's only double numbers into a table. It's a matrix. A model is a function that allows to predict maybe one column as a function of the others. So you have information, you see a house, how much could it cost? Okay, because it's not on the market, it's not priced yet, you have to make a guess. Okay? So it's a function that takes those columns and returns the last one. It maps a number of doubles on one double. Can hardly be much complicated, right? Now, how do you get that function? You have to train, so looking at the data you have, to guess what would be the right function. So, training a model is a function that takes a data set and returns a function mapping those columns into this prediction. Okay? So that's why I introduced this concept using Scala syntax, kind of, because they match very well. So who is a Scala developer here? Yeah, so some follow me. But I guess the idea here is very simple. You have tables of numbers, there is a column that has a special position because you want to predict it. You take the data set, you compute a function. I don't want to go too much into the details of mathematics or whatever, but you imagine that there's a procedure to do that. How do you know your function is good or not? And there are what we call metrics for these things. So basically we compute how far we are from the reality on some test data, and you want to, one way or another, minimize this error you make on average. And that is those kind of quantities that you compute. It's the sum of the difference between a prediction and the real value. Conceptually, pretty simple. Okay. So in red you have the prediction of the model, and in white you have the real data. So you see here a simple model, the simplest you can make. So you take your features, there are 4 of them, you multiply them by a number which we don't know yet what it is, because that will be the nature of our model. So I have 4 parameters for my model, which is a function, And so multiply this value by something I don't know yet, this, and I sum these things and I get my prediction of a number. It's hard to make more simple, okay? So if you're 10 years old, you can use this kind of models because you know multiplication and you know addition and you know they commute, they blah, blah, blah. Okay. So this is linear model. It is the first thing you do when you learn machine learning. I don't know even why it's called machine learning. Okay, it's a regression. So people did that on paper in the 16th century to compute the positions of the planets in the sky. So, I will skip that one. It's about the procedure to get to this set of parameters, but as you guess, it's optimization problem, so you have some crazy algorithm to do that, treat the data, iterate. It takes a lot of calculation, trials, and error. That's really the thing you have to remember. So you multiply stuff, you add stuff, you change a bit, and you do that again until you're happy. Something you will be hearing about if you talk with data scientists is training and model evaluation, validation. So usually you train the model on part of the data, you have a model, and you validate it's right on something else. Because what you want to do really is have a model that is able to make prediction for things he has not seen yet. Otherwise, you use the data set itself, right? Because the data is a function, you can map some columns onto the results, okay? But you don't know yet what you want to predict, so that's the subtle difference. And if you train and use the entire data set, basically you're mapping the data set itself. You don't know exactly how good it will be in the future. So that is why you have this, validation procedure, and you have other metrics for things like classification, etc. But that is maybe for later. The takeover is data is multi-dimensional array of floating point numbers. Models are basically arrays of floating point numbers, and everything you do with models is multiplication and addition on these. And that is where you have these frameworks that come into play, because you may have a lot of data and you may have many parameters. You want to train the model on millions of images that are 1,000 times 1,000 pixels. It's really huge number of calculations, but all these calculations are simple. Okay, so you want to run on infrastructure that is very good at computing things very fast. That is why you need these frameworks like TensorFlow, with basically linear algebra, that is addition multiplication libraries to run fast, for example, on CPUs or on the other specialized infrastructure architecture like TPUs, etc. So now I showed you the simplest thing, which is a linear model. When you hear about neural networks, deep learning, the building blocks are exactly what you saw before. It's just that you make hierarchies and topologies out of them. So very simple conceptually. So if you want to do that with Scala, because that is the topic, as I said, you have this framework, which is basically a set of native libraries written in C or C++. And on top of this, you will have bindings in different languages. The most popular one, where you have the most advanced APIs, is obviously Python. But when you want to serve things in real life, maybe you have constraints in the technology you will use. Maybe it's JVM or Scala in this case. So here I'm using a library. It's not so well maintained, but you could use the Java library, which is probably better maintained. The idea is to show that you use TensorFlow, whatever language you program in. The interesting thing here is that you have this code that allows you through the CNI layer to call the native C library, but you have also some parts of TensorFlow that are generated through protobuf. So maybe not everyone is familiar with protobuf, but the idea is that you have schemas and you can generate code to work with these schemas. So for example, a model that is saved in TensorFlow is saved in protobuf. That means you can use it in different languages pretty easy. It's interoperable in different environments, so you're not stuck with a snake. Yeah, that's it. This is for the workshop, an environment to work with. I wanted to tell you a bit about what deep learning is, because it's good to know that there is no real magic to that. I think it's very important. You know, data scientists, they want a high salary. They need to obfuscate what they really do, right? You have to fight that one way or another. We've seen the linear model, okay? It's a function where you take the data you know and multiply by parameters that you will compute. You sum these things and you have the result. Very simple. Now the first way to make something like neural networks is called the multi-layer perceptron. It's just combining those things where you have here one of these models, so you have all the data you have, you multiply each time by a parameter, you sum and you get a result. But you could do that a certain number of times with each time different sets of parameters, so you're computing different numbers, right? It's just different combinations that might see something different, let's say. And then these things you combine with a linear combination again, and you get another result. And this is really the essence of a neural network. So don't think of it like the way your brain is wired. This is so simple and strict, because it's IT, you know. Now you can write the mathematical function, you look like very clever, but in the end, it's just that. Okay? Just many of them. Okay. Now there are other tricks, but the essence is there. You compute many of these models, and they combine into something that is almost impossible to understand what it means. But in the end, the fact is that because you have that many parameters, you can see very different things, and we will come to that when it comes to images. Okay? So it's just that. Imagine that there were implementation of these things with variable resistors and compensators. Okay. It's so simple you can wire it manually. Now deep learning, what does it mean? It means that, oh, we have plenty of computing power, so we will add many of these things, so it's going to be deep. Okay. And actually it's also adding some topology, like if you want to analyze images, if you want to detect that there is someone in an image, how would you do that with a computer? You need something that is localization, of course, because you want to see where the eyes are. They're one on the side of the other, okay? Not one on top of the other, otherwise it would take vertical degrees. So, you have layers in your network that are wired in a way such that we look at the localization of things and we try to find different shapes at different positions, and we keep memory of these things, and then we change the scale. Oh, we've seen this little pattern that might be a lobe of an ear. Where is it compared to the other lobe or the eye, etc. So this is really how you detect things in an image, by adding layers after layers, changing the scale after the scale. So starting from 1,000 times 1,000 to 10 possible outcomes. This is the Scala code that will do that. So there's a nice API that allow you to say, oh, I have a convolution layer. That means I'm scanning the image to find different patterns. and then I try to find the patterns that are most highlighted, and then I do that again. So it's just adding layers on top of layers in one way or another. So they spent many hours trying all kind of combination. It's so clever. Now the interesting part with this is that because these people put so much effort in finding good models, and because we have now the technologies and like TensorFlow to save these models in formats that are interoperable, we have actually access to libraries of models to fill in, to resolve some well-defined problems, like finding an object in an image, recognizing speech, recognizing what is the language of text. All those kind of things are kind of commodity needs for modern, data analytics in many cases. So it can be, in a line of production, you put a camera, you will have to find cracks in things like this. Because you need a model to detect some specific shapes. It's the same signature. You have an image. It's pixels, and in the end, you want to know if there is a position where there is something wrong. Okay? So just simple things. The parameters or the complexity of the model, the different layers, should not matter. Okay? And that is the idea behind these published models that can be used. For example, here I think I show it in Scala. Before I make the demo, I will just say a few words about this. I'm using some models that come from internet. That is published. It's pretty big stuff because it's protobuf. That is pretty, how to say, verbose text containing all these parameters. It's a big file, but using TensorFlow, you can change the format of these things to something that is more binary, targeting maybe specifically JavaScript, or even lower level. You have this TensorFlow Lite that will compile these things in a very compact format, with the idea that it might be living on embedded systems. You have also ways to reduce the representation, floating point numbers. Many of them, why would you need 16 precision numbers where probably 3 or 4 decimals would be enough to go? Because anyway, you don't get 100% precision, so going from 97 to 96.6, but saving you, 5-fold representation inside, and computation can be really worth it. So there are many things you can do. I go pretty raw and wild here, so it's going to be slow, but you have to think that what I show can run probably 10 or 25 times faster with the optimization. Okay, I could run on my phone with a live video stream without problem. The idea is to show the engineering behind that. So what I will show here is a web application where I submit an image and I want to know if there is someone in this image. And to do that, I have this HTTP layer, I have the Scala Tensorflow API, and I need a TensorFlow model. So a configuration file to fetch a model from the internet. I get it if I don't have it locally. I save it locally, and then it's being loaded in the computing infrastructure, which is my CPU here, but it could be my GPU. So first one will be a bit slow, but then it's in memory and it's spitting result a bit faster. Okay. So let's go to the demo. And the code here, just in a nutshell. So, for those who like Aka, you have a root with some path. There is one path, detect, post. You post an image in PNG, blah blah blah, detect, things, okay, and return the detection. Detection is just it's loading a model somewhere, putting the data that comes from the image, making a computation here, and we detect objects, and we return a list, let's say here, believe me, don't try to understand, which contains boxes, so position of rectangles containing a score. Is it good or is it not good that it is a person? Score. Floating point numbers. I get objects. And that's what you mentioned. And then there is this blah 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 thing to download the model from internet if it's not available locally. Okay? I will start this service and then SDT to run. It would be nice to deploy somewhere, right? Okay. So I have my super client here. So it's a notebook, basically a web page in which I can edit Scala code and run it. There's a REPL in the background. Yeah, it's really messy. It's just to make sure that no one hires me as an engineer. You know, I want to remain an evangelist. Okay, so let's execute this. This is the stuff to deserialize my JSON for what is coming back from the service. I will take this image from my library of images, and I will define this function, which is my favorite, you know, Scala HTTP client. So I just post the content of the image on the endpoint, and so it's defined. I can run it. I have a function here to display the boxes in the image. I will first run the detect object on my image file. You see it's a bit slow, like a few seconds to detect things. But I see that I detect persons. Is a good score on that box. Another detection of a person is a good score, 96%. So I have 2 persons in that image, and I could display it if I wanted to. Much faster. So this is real. These are really persons. So that would be, you know, a use case. I need to know if there are persons in my field so that I know if the software has to break or accelerate. But now I have another use case. You know, I have this nice web service. I can detect people, but I want to detect faces, just because I'm not interested in those parts. Because I need to anonymize them. You shouldn't be able to recognize them for privacy purposes. Okay, so it's another use case, but it's detecting objects in images. It's the same use case. It's the same input, it's the same output. And it happens that you have models to detect faces that are very advanced because you want to, instead, you know, discriminate a cat from a dog from a person. It's, you know, detect faces in many contexts. So it's a bit harder. It's for privacy purposes, so it has to be much better. So it's a bigger model, so it will run slower, but better. So how do I do that? Well, fast forward. I change a few parameters here. So location of my model is here. It's another name, but it's still a protobuf, and it comes from another source. So I change just these parameters, and I restart the application. It's the same application, specialized to detect objects, Control C and so. SDT run. Yeah, I make a commit, I push the change, it deploys.
With the export, using an E on the export.
No. That would crash.
Xavier
Thank you. Someone is following me. I'm almost finished. Okay, so what happens now? It's a much heavier model. First execution is slow, you have to load all this, read all this graph of computations, load it in the memory bin. Okay. So no change in code, just swap the model. And if you want to do machine learning those days, combined with engineering, this is how you have to think. You have web apps, or let's say services in general, that fill in one AI task that has to be defined in such a way that the execution of the model is just like calling something to a database. Give me predictions for that image. Boom. Okay, so deep learning. So don't get confused with data scientists. This is what we really want to make clever systems and AI in modern days. So combine engineering, which the way I did kind of sucks, I know, but you get the principle. Okay. So this was the idea behind this stuff. Thank you.
Thank you, Xavier. Impressive. Do you think it looks doable to do this? We will find out, because some of you will do the Scala workshop, so you can do this stuff as well. Together with Vincent and Ravi, the guys over there. So, who wants to do the Angular workshop? I know some of you, yes. You can follow Iulia, this pretty girl over here. Yeah, just follow her. If you need to, no, did not. You're needed here, Xavier. Yeah, okay, so you can go. If you want to take, just follow her so you know where it is. You can have like a 3-minute break if you need to go to the toilet, get some coffee or something. And now we continue here with the Scala.
Semua ada macam mana?